Welcome to This Explainer. Today, we're demystifying the silent, invisible hardware that essentially runs our daily lives. I mean, have you ever stopped to think about the actual technology that lets you breeze through an airport security line or tap your phone for a coffee without even breaking your stride? We're diving deep into the architecture that bridges the physical and digital worlds in absolute milliseconds.
So, let's jump right in and look at the core magic trick making all this convenience possible. Direct data entry, or DDE. Think about the old way of doing things, manual entry. It requires constant human typing, which, let's be honest, means high latency and a ton of typos. But with DDE, we're literally extracting information straight from the physical environment into our digital systems with absolutely zero human intervention. Here's our roadmap for today. We'll be looking at the frictionless ecosystem, swipes, chips, and waves, translating the physical world, the matrix of commerce, and finally, the mechanics of vulnerability.
Starting things off with Section 1, the frictionless ecosystem, and our journey through invisible technology.
Picture your last trip to the airport to see how this invisible tech actually shapes everyday behavior. DDE isn't just one gadget, it's a massive, interlocking symphony of scanners and radio waves. Deep in the baggage routing system, hidden tags are tracking your suitcase without a single human laying eyes on it. Up at the security gate, geometric codes are instantly validating boarding passes. It's this incredible synchronized machine checking bags, verifying identities, and processing payments all at the exact same time.
Moving right along to Section 2, swipes, chips, and waves, where we talk about payment verification. And this is a perfect evolutionary contrast. Think about contact-based verification, like inserting a chip in PIN card. You physically insert a microchip, manually punch in a PIN, and the machine verifies that the data matches. It's incredibly secure, sure, but it takes a moment. Compare that to the radio wave evolution of contactless cards. You've got a tiny embedded chip emitting radio waves, firing off a payment via 128-bit encryption from up to 4 centimeters away. It's an absolute game changer for everyday convenience.
Now, the really crucial thing to understand here is the constant tug-of-war between speed and security. If we break it down, an old-school magnetic swipe is fast, but it's totally unencrypted, meaning it's highly vulnerable to data loss if it gets near a magnet. Chip and PIN gives you the absolute highest security because it requires a physical chip and human memory. But of course, it's the slowest option. Then you have contactless tap and go. It is instantly frictionless, but that speed inherently introduces a small unique risk, proximity theft. Someone with an active reader basically just has to stand uncomfortably close to you to skim your card.
Okay, Section 3, translating the physical world, focusing on optical character and mark recognition.
When we put these two optical translators head-to-head, you really see how flexibility comes at the direct cost of accuracy. Optical character recognition, or OCR, is super versatile because it tries to read actual letters and handwriting, but since it relies on a really complex software engine, it honestly struggles with how messy human handwriting can be. On the flip side, optical mark recognition, or OMR, is lightning fast and dead accurate. The catch? It's completely inflexible. It needs rigid, pre-printed forms so it knows exactly where to look for a specific mark.
Going back to our airport scenario, OCR is the exact technology customs officials use when processing your passport. The hardware and software work together to convert the hard copy text of your ID into an editable, searchable digital format. It's also the backbone of those automatic license plate readers you see on the highway. It processes data vastly faster than typing and drastically cuts down on human transcription errors. Meanwhile, OMR relies on exact coordinate logic. Think of an X and Y grid. It isn't actually reading a word. It's looking at coordinate X14, Y42, and asking, is there a pencil mark right here? Because it stores the exact geometric position of the mark, it can grade multiple choice exams, surveys, and voting forms instantaneously. It achieves incredible accuracy, as long as you actually stay inside the lines.
Next up, Section 4, the matrix of commerce, covering barcodes, QR codes, and bulk detection.
Here we have the classic 1D barcode. It is the tried and trusted grandfather of automated stock control, found everywhere from supermarket checkouts to library scanners. But it absolutely has its limits. Its physical fragility and linear nature mean the codes can be easily damaged, scratched up, or even maliciously swapped by bad actors, which poses a real administrative headache.
Now hold on to this number for a second, 7,089. That is the exact maximum digit capacity of the next piece of tech we're looking at, representing a massive exponential leap over those standard linear barcodes.
Enter the quick response, or QR code.
This is a 2D barcode made up of a high-density matrix of dark squares. Because it's a matrix, it's omnidirectional, meaning your smartphone camera can scan it upside down, sideways, whatever. And that massive 7,089 digit capacity? That allows it to do way more than just ring up a price. We're talking triggering immersive augmented reality, authenticating Wi-Fi networks, or validating your digital boarding pass right at the gate. The whole shebang.
But what about physical items moving in bulk? For things like your routed airport baggage or massive warehouse inventory, we rely on radio frequency identification, or RFID. RFID uses tiny tags made of a microchip and an antenna to capture data without needing any line of sight. Imagine an entire crate full of tagged items being scanned completely simultaneously by a single reader. It's incredibly powerful, though it does have a few hiccups, like signal overlap, known as tag collision, and it is a bit easier to hack compared to shielded contact methods.
Which brings us to our final part, Section 5, the mechanics of vulnerability and the hidden risks of a frictionless world.
So we've got to ask, is a totally frictionless world actually safe? When we stop looking closely and just let the machine scan everything for us, what exactly are we missing? Does this blind trust in automated translation leave a backdoor open for malicious actors?
This brings us to a really sneaky Trojan horse vulnerability known as a tagging. This perfectly illustrates the danger of devices that read data formats completely alien to the human eye. You can stare at a QR code all day long, but you cannot naturally read the data hidden inside that geometric matrix. You just have to trust it.
Let's walk through how this exploit actually happens in the real world, step by step. First, a scammer physically slaps a fake QR code sticker directly over a legitimate one, maybe on a city parking meter or a restaurant menu. Second, because we obviously can't read the matrix ourselves, we just trust the physical context and perform a blind scan with our smartphone. Finally, the phone faithfully executes the code's instructions. That could mean a stealth redirection to a fake phishing website or even silently downloading malware right onto your device. It's wild. A piece of literal sticker paper completely bypasses our billion-dollar digital infrastructure just by exploiting our desire for frictionless convenience.
It kind of leaves you with a chilling final thought, doesn't it? We've built this astounding architecture of direct data entry that flawlessly translates the physical world into digital action. But as our hardware evolves to become increasingly invisible, if frictionless convenience requires blind trust, who is truly verifying the physical world around you? Thanks for joining me for this explainer. Stay curious and keep your eyes open out there.